Hi, and welcome to 16.1 Classification of Matter, the first lesson in our modern physics unit. In this lesson, we talk about a lot of different terminology baryons, hadrons, mesons, leptons, quarks, antiquarks, antimatter. We have to remember all this stuff, but it's located in your reference table. So let's start by taking a look there. So there is definitely a lot of good information for this modern physics unit in general. We're going to need to know the speed of light in a vacuum. What else pops up? Definitely the elementary charge is going to pop up. We're going to talk about how 1 electron volt is equivalent to this many joules. We're going to need to know that. Not for this lesson, but we're going to need to know Planck's constant over there. Universal mass unit will pop up. And notice this, it's like, well, we don't really know what an electron volt is, but we know that it's a measurement of energy, right? So they're saying, okay, this is the energy for one mass unit, mass and energy. So there's like a conversion factor here. That's kind of crazy. All these different stuff is for modern physics, and then rest mass of protons, neutrons, and electrons. So, yep, that's on the first page. That's good to know. Unit 15 was all of this stuff. And then we have, okay, so this is going to be 16.2. We're going to do the energy level diagrams for hydrogen and mercury. But for now, we're on page 3, and we're going to be talking about the classification of matter. All right, so we have this diagram and this table that helps to define the classification of matter. So if you think back to your chemistry classes, try to think of like the smallest constituent of matter that you could think of. You're probably thinking like electrons, protons, neutrons. Those are what makes up everything else in the universe. Well, that's not the full story. In science, like we kind of go step by step, and we don't tell you the full story. We just kind of like build it up, and then you're like, oh wow, there's actually more to it. So yeah, the electrons, you can't break down electrons anymore, but actually protons and neutrons are made up of things called quarks. And here's how we organize that stuff. So matter can either be considered a hadron or a lepton. All right, so electrons are a type of lepton, but there's other types of leptons, muons, taus, and then a neutrino associated with each, which is basically a neutral version of this lepton, okay? So leptons, for example, would be an electron, all right? The hadrons are different from the leptons because they could be broken down into either 3 quarks or a quark and an antiquark. The leptons don't break down into quarks. They're just like, that's what it is. It's the base unit is the electron there. You can't break down the electron into any more. But hadrons, for example, protons and neutrons, so those are types of hadrons, right? Can be broken into quarks. So and then it breaks down even further. So you could have 2 different types of hadrons, and it depends on the quark composition. That tells you if it's a baryon or a meson. Okay, so protons and neutrons fall into the baryon because they're made of 3 quarks. So this table here shows you the 6 different types of quarks that you could have. You could have an up quark or a down quark, a charm quark or a strange quark, a top quark or a bottom quark, and there's all the different combinations, but there's 3 of them. So if you had an up, and a down quark, that means you would have positive 2/3 E plus positive 2/3 E, and then a down quark has a charge, these are the charges, of negative 1/3 E. So you have to do some addition. I'm trying to figure out up, and down, is that going to be a proton or a neutron? Does it have a charge of positive 1 E or 0 E? So we have 2/3 plus 2/3, that's 4/3. 4/3 minus 1/3 is 3/3. So 3/3 E is equal to positive 1 E. So the quark composition of a proton is up, up, down. And then if we wanted to find what the quark composition of a neutron is, pause the video and try to think. And it's only ups and downs. So what combination of ups and downs would give you the charge for a neutron? 0e. Well, did you pause the video? Let's see. If it was up, down, down, what would that give us? Positive 2/3 of the elementary charge, negative 1/3 of the elementary charge, and negative 1/3 of the elementary charge. So now we have negative 1/3 plus negative 1/3 is negative 2/3, and negative 2/3 plus positive 2/3 is 0 thirds, I guess, if we were going to be like equivalent to what we did over here. 0 thirds E is equal to 0 E, which is a neutron. So the quark composition of a proton is up, up, down. The quark composition of a neutron is up, down, down. And those, since they're made of 3 quarks, they're considered baryons, which are a type of hadron. Well, how do you get a meson? A meson, let's see here, are made of a quark and an antiquark. Well, what the heck is an antiquark? It says over here, note, for each particle, there is a corresponding antiparticle with a charge opposite that of its associate particle. So you could have an up and you could have an anti-up. And it's not written here like this is the symbol for up. They don't have the anti anything written down here, but to make it anti, you just go like that. You put a line above it, and now we have an up and an anti-up. We have a quark and an anti-quark, and those two together would give us a type of meson. There's a lot of different types of mesons that you could have, a lot of different types of combinations of quarks and antiquarks, and they're all made in like particle colliders. And the fact that they're a quark, the fact that they're matter and antimatter together means that they have a very short half-life. They're unstable, and then they convert back to energy very quickly. They decompose pretty much. So what are we talking about here? We have positive 2/3 E. That is the charge for an up particle. And an antiparticle has a charge opposite that of its associate particle. So the anti-up is negative 2/3 E. Okay, so that's what it is. And it doesn't have to be like always like down and anti-down. You could have a different antiparticle besides down. It could be anti-strange. There's a lot of different types of particles, different types of mesons there. But again, they're unstable and you wouldn't really find them occurring in nature. They would have to be artificially made. Okay, so that's like what you need to know for this topic. But just so that we know, all right, we have this section of the reference table as well. So you're jumping all around the reference table. There's a lot of information on the front page. There's a lot of information on page 3. And then these equations are on page 4, or is it 5? Page 5. All right. This one, I think, is 16.2. And then this is 16.3. And then you know this one, this is going to be 16.4. We don't need these equations for 16.1, classification of matter. We just need to reference this table on page 3. So let's get into it. Number 1 says a top quark has an approximate charge of, and then they give all the answers in terms of coulombs. So if you look back at your table, a top quark, they tell you, has a charge of positive 2/3 E. That's positive 2/3 times the elementary charge. So we have to find the elementary charge on the front of the reference table, and hopefully you still have it memorized from Unit 10. But 1 E, one elementary charge, is 1.6 times 10 to the negative 19 coulombs. So we want 2/3 of that because the charge, again, for the top quark is 2/3 times E. So for a top quark, the charge is positive 2/3 E, which is equivalent to positive 2/3 times 1.6 times 10 to the negative 19 coulombs, and then that will give us a charge of positive 1.06 repeating, so positive 1.07 times 10 to the negative 19 coulombs, which is choice C. All right, very good. Number 2, the charge of an anti-strange quark is approximately what? So we're talking anti-strange. Let's take a look at our table. Here's the strange quark. An anti-strange, which is the S with the line over it, would have a charge of positive 1 over 3e because it's the same, like mass and everything. It's just that it's the opposite charge. That's what makes it an antiparticle. So we're looking at positive 1/3 times the elementary charge. And we can do the same thing. We'll write the symbol, and anti-strange is positive 1/3 e. It's opposite the charge in your reference table, which is equal to 1 over 1/3 times 1.6 times 10 to the negative 19 coulombs, which is equal to positive, here we go, positive 5.3 repeating times 10 to the negative 20 coulombs of charge. So we're looking at choice A. A lot of different possibilities over there. Positive and to the negative 20. Cool. All right, compared to the mass and charge of a proton, an antiproton, this is just the definition of what an antiparticle is. So it's the same mass, but opposite charge. So we're looking at choice C. It's an antiparticle, so it has the same mass and an opposite charge. A particle that is composed of 2 up quarks and 1 down quark, so 2 ups and 1 down. That looks like 3 quarks to me. So look at your table. What would you call something that's made of 3 quarks? Is it a meson? Is it a proton, a neutron, or a positron? All right, so 3 quarks, okay? And then it was either a proton or a neutron. I think they said it was an up, and a down, right? We already did that. So positive 2/3 E, positive 2/3 E, and negative 1/3 E. This is 4/3 minus 1/3 is positive 3/3, which is equal to positive 1e. And a proton has a charge of positive 1e, and it's made of 3 quarks. So a proton is the best answer of those 4 given. A meson, remember, is a quark and an antiquark, not 3 quarks. So that's definitely out. So this is a quark and an antiquark, definitely not that. A neutron, we did that one before. That's going to be an up, a down, and a down. 2/3 plus negative 1/3 plus negative 1/3 is 0e. And then a positron is going to be it's like an anti-electron. So that is positive 1e as well. But a positron is actually a type of lepton. A positron is the anti-electron. It's another word for an anti-electron. So if you wanted to make a symbol for it, I guess you could call a positron like that. It's the anti-electron. And again, it's a type of lepton, which are not made of quarks. So it wouldn't be an up, up, and down, even though it does have the same charge as a proton, which we calculated just now. So the correct answer is choice C. The composition of a meson with a charge of -1 elementary charges could be, and then they give you 4 choices. So it's a meson, and you look at your table. Mesons are made of a quark and an antiquark. 2 things, a quark and an antiquark. So we can eliminate some answer choices. Since it's a meson, it cannot be choice B, that's 3 quarks, or D, that's 3 antiquarks. We're looking at a quark and an antiquark, and a quark and an antiquark, and we need to calculate the charge because we're looking for -1e. All right, so we have a strange and an anti-charm. Or is it going to be an up and an anti-bottom? Let's take a look at our table, get those charges. Okay, so I rewrote them, strange and anti-charm, up and anti-bottom, just so that we could see them here. So for strange, that's going to be -1/3 E plus an anti-charm. So this is the charm, and anti-charm is negative 2/3 E. So that's looking pretty good. Negative 1/3 plus negative 2/3 is negative 3/3 E, which is equal to negative 1 E. So that's the charge for this. Oh, but did they say positive or negative? Let's see. So an up is positive 2/3 plus an anti-bottom. Here's the bottom. An anti-bottom is positive 1/3 E. It's the opposite charge. So this is so we're going to have a negative option and a positive option. So 2/3 plus 1/3 is positive 3/3, which is equal to positive 1 E. So what did they want, negative or positive? It looks like they're looking for negative 1 E, so that would be a strange and an anti-charm. Cool. Number 6, it's worded a little bit differently. It says a particle unaffected by an electric field could have a quark composition of what? So if it's unaffected by an electric field, what does that mean in terms of its charge? That means its charge must be 0. It must be neutral. So we're looking for something that gives us 0E. 0E. I was going to write a positive sign, but 0E. Okay, so charge, strange, bottom, 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 up, down, charge, or up, up, down. Let's take a look at our table. Okay, so here are our 4 answer choices. Let's go through each one. Charm is positive 2/3. I'm going to forego the E just for sake of space. And then we have strange, minus 1/3, minus 1/3. All right, so 2/3. Well, this is minus 2/3. So actually, that's going to give us 0E right off the bat. Sweet. Bottom has a charge of negative 1/3. So negative 1/3. You can see where this is going. That's negative 3/3 or negative 1E. How about up, down, charm? Okay, up is 2/3, positive 2/3. Down is negative 1/3. Charm is positive 2/3. Let's see, 2/3 plus 2/3 is 4/3. Minus 1/3 is 3/3. 3/3 is positive 1E, where I come from. And then up, up, down, 2/3. Oh man, getting ahead of myself. 2/3 plus 2/3 down is negative 1/3. So 4 minus 1 is 3, divided by 3 is positive 1 again. That's the composition for a proton, up, up, down. Cool. So we were looking for something that's not affected by an electric field or has a neutral charge. That's going to be charm, strange right here. Okay. Number 7. It says a lithium atom consists of 3 protons, 4 neutrons, and 3 electrons. So periodically throughout this unit, they'll say like a lithium atom or like it could be anything, like you've never even heard of the type of atom before. But they'll always give you enough information about that weird sounding atom so that the name of it actually doesn't matter. It's just kind of interesting to know what the name of the atom is that they're talking about. They want to make it like make sense. But really what we're focusing on is not the lithium part or any other the weird names that you might see on a future question. Let's focus on the 3 protons, the 4 neutrons, and the 3 electrons. And they're asking, this atom contains a total of how many quarks and how many leptons. So we have to remember protons, neutrons, and electrons. Let's look at our table quick. Protons and neutrons are consisting of 3 quarks, and an electron is a type of lepton. So if you didn't write like these things in here, and this here, and this over here, I would write that in if you have a paper version of the reference table to remind yourself that protons and neutrons are made of 3 quarks and an electron is a type of lepton. So let's use that knowledge to answer this question. So I have 3 baryons, 4 baryons, and so that's a total of 7 baryons and 3 electrons, so that's 3 leptons. But they didn't say like the baryon option is not an option. They're talking quarks. Well, we know that baryons are made of 3 quarks. So times 3 quarks is equal to 21 quarks total for the protons and the neutrons together, and then 3 leptons. So that's going to be choice D. Cool, 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 cool. Okay, so number 8 says particles in a nucleus are held together primarily by the strong force. That's what we're looking for. That's just something you kind of have to memorize. Because if you think about a nucleus of an atom, 2 protons, and then maybe there's 2 neutrons in there, and then the electrons are out here somewhere. Let's say it's a neutral atom. Right, it's got 2 electrons. Okay, well, in the nucleus, the particles in the nucleus of the atom, what's holding those things together, right? Because if you forget about the electrons for a second, these 2 protons are positive and the neutrons are neutral. So since these 2 things are positive, they should be repelling each other. And there is a repulsive force. The electrostatic force is repelling, but there's a stronger force holding the nucleus together, and that stronger force is called the strong force. So there's like different fundamental forces at play within the nucleus of the atom. Cool, 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 cool. Number 9. Which particles are not affected by the strong force? So we just said, like in the nucleus of the atom, the protons are held together by the strong force. It overcomes the electrostatic force that they feel of repelling each other, and the neutrons are also in there being held together by the strong force. The electrons are not affected by the strong force because they're not in the nucleus. And if you think about it, protons and neutrons, we said, are types of baryons, which are considered hadrons. So these 3, A, B, and C, are affected by the strong force. Electrons are not in the nucleus of the atom, and they're not affected by the strong force. Okay, baryons may have charges of. This one's a little tricky. You have to think about it. And one thing to keep in mind is that baryons cannot have a fractional amount of charge. Like the total charge for that baryon has to be 1, 2, or, well, not really 3, but it has to be an integer number is the word I'm looking for. An integer. It can't be a fraction. So it cannot be a fraction. So it can't be A, can't be D. Could it be B? Well, it can't be B because you can't get 3 quarks to have positive 3e. If the 3 quarks added up to positive 3e, that would imply that each quark had positive 1e. And if you look at your table, none of these have a charge of positive 1e. The maximum you could get for a quark is positive 2/3 e. So you cannot add 3 quarks together and get a total charge of positive 3e. That means choice B is out as well, and choice C is a valid answer because you could have a quark composition that leads you to positive 1e or negative 1e. All right. It doesn't have to be a proton. Like protons are positive 1e, and you might say, oh, a neutron is 0. How could you have negative 1e? I thought that was a electron, leptons. Well, there's different types of baryons, besides just protons and neutrons. There's other types that are made of 3 quarks, and you could have, for example, like a down, down, down would give you negative 1/3, negative 1/3, negative 1/3, and that would give you negative 3/3, which is a valid charge for a baryon because it's made of 3 quarks. Okay, 11 and 12 have to do with this table here. They give you the symbol for a bunch of different types of subatomic particles. They give you the name of those particles. They give you the quark content. That's cool. And they even calculate the total charge for you. They didn't have to. We could have calculated that. But that was nice of them. And then they tell you the mass in terms of a giga-electron volt per c squared, the speed of light in a vacuum squared. And this actually kind of, if you're wondering about this is a unit of energy, and this is a unit of, well, this is not a unit. This is c squared. It's a quantity, the speed of light in a vacuum squared. So it's actually kind of talking about E is equal to mc squared. And if you solve for mass, you could consider mass in terms of the energy per speed in light in a vacuum squared, and the energy happens to be not in joules and not in electron volts, but giga electron volts. So that's what's going on there. It's just a way to measure the mass. But we didn't do E equals mc squared yet. So let's see what this question is even asking. It says all the particles, number 11, listed on the table are classified as mesons, antimatter, hadrons, or leptons. Okay. So are they, well, let's look at the quark content. They're all made of 3 quarks. So we're thinking either baryons or hadrons. Definitely not mesons, because that's a quark and an antiquark. Antimatter, that's very vague. You could have different types of antimatter. Leptons, not a lepton because it's made of quarks, so it's a hadron. All right. Another valid answer would have been a baryon. Okay, because baryons are types of hadrons that are made up of 3 quarks. And number 12 says, which particle listed on the table has the opposite charge of and is more massive than a proton? Ooh, nice. So we're looking for 2 things. We're looking at the charge. We want the opposite charge of a proton, and we want something that's more massive than a proton. So obviously the charge is positive 1e. We're looking for something that's opposite of positive 1e. So far we're looking at an antiproton and omega. Okay, so which one of those? So antiproton and omega. The other thing we were looking at was we wanted to be more massive. Well, an antiproton is going to be the same exact mass, all right, but it's just opposite charge. That's the nature of it being an antimatter. It's the same mass, opposite charge. So here's the mass here, and for the omega, it has more mass. So we're looking at the omega particle as the answer to this question. Okay, I think that's about it. Yeah. All right, so that was a lot of fun talking about all these different, like, weird sounding things: mesons, hadrons, baryons, leptons, and then quarks and antiquarks. But it's good to have like a good foundation in this vocabulary as we move forward in the modern physics unit. Anyway, that's about it. Have a great day.